Students, in the previous class we have seen the galvanic cell, right? So what is galvanic cell? The galvanic cell is nothing but the conversion of chemical energy into electrical energy. We call it as galvanic cell, and we have seen the process of the galvanic cell also. So now I am going to describe you about the, if you apply some external source without applying external source, with applying external source, so what are the condition is going to happen here. So the first case, if you have been observed here, see here we have taken a two beakers, that is zinc, another one is copper, right? So coming to here, this is a salt bridge. So coming to here, this is an external source which is greater, means what here, the external source is greater than 1.1. 1.V indicates what here, the EMF of this cell. EMF is nothing but electromotive force. The EMF of this cell, if suppose we are having, means at 298 Kelvin, 1 atmospheric pressure and 1 concentration, so the standard potential will be here 1.1, that indicates 1.1 V. So if the external source is greater than 1.1 V, means what here, coming to here, the source whatever we are applying, that is less compared to the 1.1. So if suppose if it is happening, so what happens, it will donate electrons to this one and this one will donate electrons, so means it will flow opposite side, both plus and minus, means what, this will flow and this one will also flow. So this opposite direction it is going to flow the current, that one we call it as a first condition. Coming to second condition. So what is second condition? If suppose the external voltage whatever we are applying is very much less than 1.10, means what happens here, the reaction is not going to happen, the current is not going to flow. Why? Because here, why it is not going to flow, here external potential is equals to 1.1. so this is the second case. If suppose we apply some external source 1.1, means if suppose if we are keeping battery, okay, so what happens then here, if it is more than the voltage, means here the reaction is in the opposite direction. So at that time what happens, means in galvanic cell what happens, chemical energy is converting into electrical energy, but coming to here what happens, electrical energy is going to convert into chemical energy, which will act as like a electrolytic cell, electrochemical cell. So this is nothing but the three conditions, which is also known as reversibility of Daniell cell. Okay, so and we can determine the equation how to write cell representation, how we can represent the galvanic cell also. See here this is the equation. For example, Zn plus 2. Okay, so the middle between semicolon we can use, or we can use it as vertical line. Okay, so here the whether it is semicolon or vertical line we can use it here. So here this one indicates what here, double line indicates, parallel lines indicates what here, the parallel line indicates here salt bridge. So and this one is a copper. Okay, so this is the way of representing the galvanic cell equation. If you take platinum in the presence of hydrogen, so here see, this one indicates what, this is the representation of the galvanic cell representation. So this is nothing but galvanic cell and the conditions of the Daniell cell. Let us see the differences between galvanic cell and also electrolytic cell. The galvanic cell is also known as electrochemical cell. So what is galvanic cell? Conversion of chemical energy into electrical energy. Then what is electrolytic cell? Electrical energy into chemical energy, we call it as electrolytic. So in this cell what happens, anode acts as negative, cathode acts as positive. Coming to here, anode acts as positive, cathode acts as negative. Why? Because here we are applying some extra source, that indicates what, battery. Okay, so it is a spontaneous redox reaction, we can say it is non-spontaneous. Okay, so why we say it is a spontaneous, it itself flowing the current, but coming to here we are applying some current, that is battery. Okay, so here the two electrodes we have kept in two different vessels, but coming to here we are going to keep in a electrodes in same vessel. So here two half cells are taken, here only one electrolyte is taken. So this is nothing but the difference between the electrolytic and electrochemical cells. So now we want to find the electrode potential. So what is the electrode potential? So the electrode potential is nothing but here the distance between the, so if you have been seen here, the distance between the two electrodes, we call it as electrode potential. In this we are having single electrode potential. The single electrode potential is nothing but what here we are taking as a standard conditions. Okay, so here what we are taking, standard conditions we are going to take. What are the standard conditions? So the standard conditions indicates here at 298 Kelvin 1 atmospheric pressure and the concentration is 1. That one we indicates what here, the electrode potential is taken as 0. So means what here, reduction half cell and oxidation half cell will be the 0. That one indicates single electrode potential. So now what is standard hydrogen electrode? The standard means I have told you, standard means what here, 298 Kelvin 1 atmospheric pressure, and here still what we can say here, 298 Kelvin 1 atmospheric pressure and the concentration is 1 m. That's why we are saying what here, standard. So what I'm saying, if you want to find only for zinc, okay, if you want to find only for zinc the electrode potential value, and how we can find for only for zinc the electrode potential value, we cannot find that one, right? So for that we are taking a reference electrode or standard electrode or normal electrode. That one only we call it as here hydrogen electrode. With this, in place of copper we are going to take this one as a reference electrode. We have taken in galvanic cell zinc and copper, right? So there we are going to remove copper and we are taking here hydrogen electrode in place of copper. And if you want to find out electrode potential for copper, then you have to remove zinc and you have to place it as a hydrogen electrode. Okay, so this is the thing. So let us see the construction of the hydrogen electrode. We are taking in a vessel. So in a vessel, it consists of HCl solution at 25 degrees centigrade. 25 degrees is nothing but 298 Kelvin. 25 plus 273 we get 298 Kelvin. Okay, so to this we are having a platinum wire. This platinum wire is coated with again platinum only. This platinum wire. Okay, sorry for the disturbance. So now what happens, this platinum wire is placed here, and here this upper cover we call it as electrode cover, and this is a platinum wire, and we are applying some H2S gas with 1 atmospheric pressure, means we are sending H2 gas here, okay, to the electrode. This H2S gas is present at the platinum, and also it is present at 1 atmospheric pressure. And this hydrogen gas, what it is observing, platinum is observing. Okay, so now what happens here, so whenever it is observing and coming down as a bubbles, so this bubbles where it is in mixing hydrogen chloride, so these two are mixing, no? So means what, H2S is losing electrons and HCl is absorbing. From this HCl, H is going to absorb, right? H plus ions, means what, it is losing electrons means it is taking oxidation, it is gaining electrons means it is reduction. Okay, so now let us see half cell reactions. So if you have been seen half cell reactions, or I have told you single electrode potential, the oxidation and reduction potential will be 0 volts. That's why we say it is a single electrode potential. Okay, so now H2S is losing electrons, no? This is going oxidation, and H plus from hydrogen chloride, H plus is absorbing electrons, that is it is forming as a H2, it is reduction. Okay, so this standard hydrogen electrode we are going to use as a reference electrode. Why we are using reference electrode? To know the electrode potential of the other electrode. So that's why this is the method we are going to use for a standard hydrogen electrode. So this is nothing but standard hydrogen electrode. Okay, next topic. So these are the standard electrodes. Okay, I think you can see. So for copper, so see here, these are the values we are going to get. When you determine the EMF of this cell, we have to take these values for the problems. Now let us see determination of electrochemical cells. So means what? Cell potential. So what is cell potential? The distance between the electrodes. Okay, not difference. The distance between the electrodes, we call it as cell potential, and we are going to calculate EMF of a cell. The EMF of this cell indicates what here? EMF of this cell is nothing but E naught cell, electromotive force, the standard cell. Okay, so this E naught cell is nothing but what? Reduction potential of the reduction half cell minus reduction potential of the oxidation half cell. So means what we can say here? Reducing means reduction reaction minus oxidation. This one we call it as EMF of this cell. Okay, so means what we can say here clearly? ERHS minus ELHS we can say. So we have taken oxidation and reduction. Always the reduction should be written in the right hand side, so left hand side, and oxidation should be written in the right hand side. Okay, so this is nothing but, so here we have taken an example. See what is the question they have given? Calculate the EMF of a cell in which the reaction takes place at different electrodes. So he has given two half cells. For zinc they have given minus 0.76, for silver they have given minus 0.7. So coming to here, we have to find the EMF of this cell. EMF of this cell is nothing but E naught cell. So is equals to reduction potential of, so this one it is gaining, no, so this is a reduction half cell. So it is losing electrons, no, so this is a oxidation. So coming to here, E cathode minus E anode. So means what? 0.79 minus of minus 0.76. So by doing plus we are going to get 1.55 volts. So this is the way of calculating the EMF of this cell. Okay, by using anode and cathode reaction also we can use here electrode potential, and also by using redox reactions, oxidation and reduction reactions, also by using this one we can use this one. And predicting the reactivity. Reactivity is nothing but what here? By using their elements. Okay, by using their atoms also we can use this EMF of the cell. The EMF of the cell. Next, we are having different types of reversible reactions. So there are four types of, what are reversible reactions? Generally, what is reversible reaction? Cell consists of two electrodes, right? So the reversible cell consists of what? Two reversible electrodes. Single electrode is a electric conductor with electrolytic conductor. Okay, it may be metal, or it may be a gas, or it may be a salt. So like that we are going to have different types. So there are different types of reversible electrodes. One is metal ion electrode, another one is gas electrode, another one is metal insoluble salt ion electrode, another one is inert metal oxidation reduction electrode. So these are the four types we are having. So metal electrode means we have taken example as galvanic cell. That one we can take it as. So means what? It consists of two metals. That is, electrode consists of metal with solutions. Means what we can say here? Zinc and copper we can take it as metal electrode. Okay. So next, gas electrode. So gas electrode is nothing but what? We are having platinum. Now only we have seen standard hydrogen electrode, right? That one indicates gas. So one electrode will be a metal, another electron will be a gas. So means what we can say here? It consists of gases continually pass through solution at 1 atmospheric pressure. Gases always a pure conductor of electricity, we can say. Sorry for the disturbance. So for this what we can take here? Platinum, gold, graphite. Okay, so these are the things we can take. So example, just now we have seen the standard hydrogen electrode. That one we can take it as here. Okay, so here three types they have taken gases. One is hydrogen electrode, another one is oxygen electrode, another one is chlorine electrode. So coming to hydrogen electrode, see here, it is losing electrons and also it will gain electrons in the presence of HCl, which we have seen in the standard hydrogen. Here platinum we are going to take. And coming to oxygen, here also oxygen. So in this electrode what happens? Oxygen is going to bubble through a solution of hydroxyl, means NaOH, KOH. That one we can take at 1 atmospheric pressure. Here also platinum we are going to take. Next one what we are taking here? Chlorine electrode. So chlorine electrode is also bubbled with a platinum and HCl we are going to use. Okay. So these are the gas electrode. Gas electrode is nothing but what here? Here the hydrogen is going to absorb at the platinum, and here we are going to get over here is it is absorbing, means it is going to undergo reduction. One electrode will be a gas, another electrode will be here metal electrode. Okay, so coming to next one, metal insoluble ion electrode, means what? Just we have seen now first one, metal ion electrode. So now this is insoluble electrode, means it is going to form the precipitate over here, right? So what it is going to form? Precipitate it is going to form. So now, so means what we can say here, it consists of metal with one sparingly soluble salt of a solution of a soluble salt having common anion. Means what we can say here, for example, if you are taking HCl, mercurous chloride and KCl. So KCl is a solution. Okay. So here electrode consists of mercury. It is which is insoluble, mercurous chloride, and a solution of potassium chloride which is having a common ion, chlorine. What we can say here, common ion effect is undergoing, we can say no. So in this mercurous chloride is going to lose an electron. Okay, so what happens after losing? It can lose electrode and also it can gain electron. Mercury can act as anode and also cathode here. So what is an anode and cathode here? Anode is nothing but negatively charged particle. Cathode is nothing but positively charged particle. We can say anode and cathode. So now, if suppose it is going to act as an anode, so what happens? The current flow from left to right. Okay. So means what? It can lose electrons here. It is undergoing reduction. So then if it act as a cathode, what happens? It will flow from right to left. So means what we can say here? So what we can say here? So it is gaining electron. So means what happens here? Reduction is going to happen. ఒక్క నిమిషం. So see here. Sorry for the disturbance. So we have seen inert metal oxidation reduction. So means what? This is reduction. Redox reactions we can say. So in this what happens here? It is an inert electrode. Means what here? Here platinum is gold. Both together combined in a solution which contains both oxidation. Redox means what? Both reduction and here oxidation is going to happen. In that we are going to mix here platinum and gold. Okay, any of the thing we can inert here. Inert metal act. Inert metal is nothing but what here? Noble gas element we can say here, means which is an s orbital containing. Okay, so then the electron from the reservoir can be oxidized first. After that what happens? It changes into reduced form. For example, here we have been taken Fe plus 2. It is changing into Fe plus 3, which is losing an electron. So this ferrous or ferric ion, so it can take up the electrons, it give the electrons. So these are the 4 types. What is the first one? Metal ion electrode. Second one we are having as a, what is the second one? So second one is nothing but here metal gas electrode. Third one metal ion electrode with insoluble set. Fourth one is inert metal oxidation reduction electrode. Okay, so next one, derivation of Nernst equation. So let us see here derivation of Nernst equation. So generally the Nernst equation is nothing but what here it is related with electrodes. Okay. So electrode potential, basing upon the electrode potential and concentration of ions, we are going to explain the Nernst equation. So let us take a redox reaction. Consider A plus B gives rise to C plus D. So according to chemical law of equilibrium, what we can say, the ratio of the concentration of products to the concentration of reactants. So here K indicates equilibrium constant and concentration of products to the concentration of reactants we are writing. So this is indicated as like this. From Gibbs equation, what we can write here, delta G is equals to minus NFE. Okay, so if you are representing as a cell, it is going to write it minus NFE cell. Okay, so delta G naught. Okay, so now, but we know that what here, delta G naught is equals to delta G cell equals to delta G naught plus RT log K. So this is the equation actually we know. Okay, so with delta G cell we have seen here. What is the delta G cell? Minus NFE cell. So this NFE cell can be written as like this, minus NFE naught. So delta G naught means we are going to get minus NFE naught plus RT log K is nothing but products by reactants. When you divide both sides with RT by NF, so then we are going, NF will get cancelled and we are going to get here E cell is equals to E naught minus this minus will come this side, RT by NF log P by R. So where R is gas constant value 8.313 kilojoule and T is standard temperature in Kelvin 298, where N is number of moles, log value 2.303 to the base 10, Faraday constant is 96,500. So finally the Nernst equation what we are getting here, depending upon the electrode potential and concentration of ions we are writing. By doing calculation we are going to get 0.059. So now what we have to see means here, for metal electrode, for non-metals. So if you take metal electrodes, this is a reduction process, right? So for metal electrodes what happens, products and reactants. Here N electrons, no, so that's why we have taken as N. So for here M is concentration is unity, I have told you, standard at standard temperature, that's why M we have taken 1. So instead of writing this one we have taken C. And in the same way for non-metals, A plus N electrons gives rise to AN minus, products by reactants, and here log A minus, where concentration of A will be 1. So this one also can be written as C. So this is nothing but derivation of the Nernst equation. Okay. So now let us see how to find out for metals and non-metals. I have told the equation. No? So Zn we have taken. Here how many, in place of N what we are going to write? 2 electrons. So in place of N we are writing 2 electrons, products by reactants. Okay. So this is the thing. And if you want to change it upward, so means what, here Zn will be 1, so then A Zn 2 plus, then it is taken as a plus, so this one went upside, so means what happens, here we are going to get plus. At the same way here 2 electrons, it is running the reduction potential. This is for metals we have been spoken. If suppose if you use hydrogen electrode also same thing it is going to happen. Okay, so this is the derivation of the Nernst cell. Next one, next final topic is potentiometric titrations. Potentiometric titrations is nothing but what here generally it undergoes electrode potential depending upon the concentration of ions, whether it is reversible or irreversible. That one we call it as potentiometric titration. Here it undergoes three types of titrations. One is redox titrations, acid base titrations, another one is precipitation titrations. So here the potentiometric titration is nothing but a change in concentration, and here pH value changes. Okay, so this all is going to changes. So the measurement of potential by addition of some indicator, yes or no, if you want to do here HCl and Na2CO3 titration, what happens? We are adding some methyl orange indicator, means some external source we are adding. That one indicates what? Here potentiometric titrations. So means what? We are changing in potential at the end of the reaction. So that's why we call it as what? It is potentiometric. So by using EMF measurements, acid base, oxidation reduction, and also precipitation, can give correct values for this precipitation potentiometric titrations. Okay, so these are the advantages. So now let us see acid base titrations. Acid base is nothing but we are having strong acid, strong base, weak acid, strong base, strong acid, weak base, weak acid, weak base. We have seen conductometric titrations, that examples we can take, but here we are adding some indicators here. Okay, so for acid base titrations, for strong acid, strong base, and weak acid, weak base, we are not going to take it as a indicators. Why? Because they already are strong acids and strong bases. Because of that reason, we are not going to add any indicators. But if you have been taken here weak acid and strong base and strong acid and weak base, we are going to use phenolphthalein indicator, which is going to use the here pH value. It is going to measure. Okay, so it is going to measure pH value. What is the pH? Concentration of hydrogen value we are going to maintain at 25 degrees centigrade. So this is the graph we are going to get on x-axis, and on y-axis we are going to take here. Next, precipitation titrations. Precipitation titrations is nothing but what here? This is also known, which is going to form it as a precipitate, which is also known as here gentometric titration. Why? Because we are going to use it over here is silver nitrate. Okay, mainly silver it is going to use. That's why we say it is a precipitation titrations. In these different types of theories we are having, Ostwald theory we are having, and also phenometric theory, which is used for precipitation titrations. Next one, redox titrations. For this we are not going to use any indicator, but here also we are not going to use any indicator. Why? Because they itself is going to act as an indicator. But for one titration, for cerium and iron, we are going to use an indicator here. Okay, so some reference electrode we are going to take phenolphthalein. So for that, these are the different types of titration which will be used in the potentiometric titration to measure the EMF of the cell. Next, fuel cells. So fuel cell is nothing but what? In the intermediate we have learned already. So fuel cells is nothing but here fuel cells which converts chemical energy into electrical energy. We can say secondary battery. Okay, we are having two types of battery. One is primary battery, another one is secondary battery. So secondary battery is nothing but what? Which will be charged, recharged again. So that one we call it as secondary battery. So here fuel cells is also same thing. Okay, so in olden methods what happens means here heat is produced by liberating steam. Okay, so it will liberate steam, and it will also use it for turbines to electrical generators. So for generators mainly it is used, and the fuel is going to use, and here the fuel is going to waste. So that one is the olden method. But coming to the modern method, we are using hydrogen oxygen as a fuel cell for combustion of fuels, we can say, which the chemical energy which convert into electrical energy. So here if you have been seen diagram, so this is the porous carbon electrodes. So one is anode, one is cathode. It consists of KOH, means potassium hydroxide solution, so which act as an electrolyte here. Okay, aqueous solution. So this is an electrolyte, and here O2 gas we are passing, H2 gas, and here it is giving H2O also. Okay, so this two porous tubes, what happens? Platinum or silver or gold, which is going to act as cathode and anode. And coming to here, we are having half cell reactions. At anode what happens? That hydrogen is going to absorb, hydrogen gas is going to absorb OH minus ions, and it will give water molecule. It releases water molecule. And coming to here, what happens? The oxygen is going to absorb water molecules. It release hydroxide ions. Then the net overall reaction is going to get this one. Okay, and the EMF value we are going to have over is 0.9. So this is the thing is going to happen in the fuel cells. So here what happens, the hydrogen oxygen gases are bubbled by a porous carbon electrode. So the potassium hydroxide solution. So this is nothing but the fuel cells, and also the fuel cells is used mainly for here main of the advantages here, pollution free working, we can say. It does not produce byproducts also. Okay, so continuous energy it is going to give here, H2O2. And also here mainly space programs, we can say. And also here it converts electricity, it produces electricity by using chemical energy. So what are the difficulties we are getting here? Some technical problems we are going to get. So the catalyst whatever we are using, it is very cost, and also mainly it will rust. Corrosive is nothing but the electrolyte will become rusted particle. So gases fuels should be always at low temperature, high pressure is very difficult. So this is nothing but what here, oxidation half cell and reduction half cell. So this is nothing but fuel cells. By this electrochemistry is completed. In the next class we can see chemical kinetics. Thank you.